Hello and welcome. This video tutorial is going to help you with work, energy, and power problems. There are 8 problems we're going to work on today. Let's have a look. The first question is work, horizontal force with no friction. Question 2, work, horizontal force with friction. Question 3 and 4 are work due to a force at an angle. Question 3, no friction. Question 4 with friction. Question 5 is horizontal net work. Questions 6 and 7 relate to graphs, force position graphs, okay? And the area underneath those graphs represents the work, so we'll be doing that calculation too. And then finally, question number 8 deals with the concept of mechanical power, okay, which is relating to the rate at which work is done or work divided by time. So let's go ahead and have a look. Our first question is horizontal force, no friction. So when we open up our problem set, go ahead and put in your name. Okay, you're going to be given a mass, you're going to be given a force, and you're going to be given told that the box starts from rest. Okay, and you're going to be given the distance. For me, it's 199 centimeters. So record all that. All right, recall that to move from centimeters to meters, you got to move the decimal twice to the left. So 1.99 meters, right, is that. Okay, now in step 2, we're going to give the forces acting on this. Okay, we've got our applied force, F, that's the 4.6 newtons. There's no friction. You do have normal force, and you do have weight. Okay, so we're going to calculate the work done by friction, and then we're going to calculate the work done on the block. So let me see. You can see we're entering the work done and then the final velocity, okay? Now, it's weird. It's saying find the work done by friction, but no, it's going to be the work done by the applied force, by F. So there's no friction in this problem. Okay, so how do we calculate work? Well, work is equal to a parallel component of force times distance. Okay, well, that's going to be 4.6 newtons times 1.99 meters. Okay, in my case, anyway. Go ahead and figure out yours. All right, I'm getting about 9.15 joules. Go ahead and enter in as I go. Okay, now the final velocity, okay, what I'm going to do to get the final velocity is this. The net work is equal to a change in energy. Specifically, in this case, it's going to be a change in kinetic energy, which means that net work, which is going to be the work I calculated, is going to be equal to kinetic energy final minus kinetic energy initial. But your object started from rest. So that is our equation there, which basically means the work is equal to 1/2 mv squared. Solving for speed, we'll multiply by 2, divide by mass, and then we'll square root to take care of that. 2 times the kinetic energy over the mass, plugging in. We have 2 times the work is the kinetic energy over the mass, which in my case is 4.6. Just double check. Yes. All right, I'm looking at about 1.99 meters per second squared. Okay, hopefully you were able to get question number 1 correct. If so, on to question 2. Now, question 2 is a similar problem, but this time you're going to be dealing with friction in the problem. So you're going to be given the coefficient of friction. We're going to find the work done by tension, which in my case is 5.1 newtons. We're going to find the work lost by friction. Now, technically, the work done by friction is a negative value. Do not enter in negative values for energy, okay? Enter in the absolute value. We're given the distance, and we're given the mu. So record everything you're given. Okay, there's friction going back this way, which I'll have to calculate. Mu in the problem is 0.1. The distance traveled is 125 centimeters. Okay, that right there is going to be our distance. So we're going to draw in the four forces. We've got tension, normal force, weight. You can see normal force balances weight, so that's going to be mg as well, and then friction. Friction equals mu times normal force. So let's calculate the work done by tension. So work done by tension is going to be tension force times distance, okay, which is going to be, in my case, 5.1 newtons times 1.25 meters. .38 joules. Okay, now we're going to find the work done by friction. So first, let's find the force of friction. Mu times normal force, 0.1 times the weight, mg, so 3.6, right, times 9.8. All right, now about 3.53 newtons of force, which means the work done by friction is going to be friction times distance. Technically, it's negative friction by times distance, but let's not worry about the sign of the value. This distance, 1.25, so it's the same distance. Okay, about 4.41 joules. .37 or 38. 4.41. Now we're going to find the final velocity. So to do that, we know that the net work is equal to a change in kinetic energy. The net work is going to be the difference, right, in your works. Okay, now work equals, right, the final kinetic energy. So 1/2 mv squared times by 2 divided by mass, and then the square root. Okay, let's enter those values into the problem. 1.05. All right, and there we go. Again, hopefully you were able to get question number 2 right as well. All right, on to question 3. Question 3 is force applied at an angle. No friction on the tabletop. So let's draw. Okay, we got the 160. Okay, so I think I have everything. So now, find the forces acting on this. Got the weight. A smaller normal force. I have this force applied up at an angle, F. I have its horizontal component, and I have its vertical component. There's theta. The blue component is F cosine theta. The horizontal component is F cosine theta. The vertical component is F sine theta. And we had no friction in this one. If we have friction, it would go back this way, but no friction, no problem. All right, so a couple of things. Number one, I need to be able to find the work done by, I need to find the normal force, because it's asking me to find the normal force, the work done by tension, and then the final velocity. So to find the normal force, okay, think about what I'm doing. Normal force is a vertical force, right? It's a vertical force. You can see that right here. And so I'm going to use my Newton's first law analysis because I know I'm not accelerating vertically. That tells me force up equals force down. And going up, you guys should be able to see that we have two forces, normal force and F sine. So normal force plus F sine equals one force going down. Okay, we'll call that mg. So if I'm trying to solve for normal force, I'm going to have to subtract F sine. Normal force would be mg. We subtract F sine from both sides. Let's see, minus F sine. Let's plug into that. So we have a mass of 0.7 minus okay. The work done by tension is going to be tension cosine theta, that's the force cosine theta, okay, times your distance. So we're going to go 4.5 cosine of, I forgot my angle already, 37.3, I think it is. Yeah. Times the distance, which is 1.6. Okay, about 5.73 joules. All right, now to find the final velocity here, we know that the work done by the horizontal component of tension, which is going to be T cosine theta, is equal to the final kinetic energy, 1/2 mv squared. So, you know. Okay, and then so V is the square root of 2 times the work done by T cosine theta over the mass. Okay, got a little crossed up there a second. So 5.73 times 2 divided by 0.7, looking at about 4.05 meters per second. Okay. All right, and it worked. Okay, on to question number 4. So question number 4 is the same problem. The only difference is we have friction coming back sides. So we've got work equals mg. You've got a smaller normal force. You've got tension up at an angle, tension cosine theta, tension sine theta, and friction equals mu times normal force. Okay. Okay, so first calculate the normal force. Remember, force vertical, that tells us normal force plus T sine, or F sine, whichever you want to call it, is equal to mg. So normal force is equal to mg minus T sine theta. Sorry, I forgot to put in my values. Okay, 2.2 kilograms. Six newtons. 24.5 degrees. 1.06. So 106 centimeters is 1.06 meters. And the coefficient of friction in my case, mu, is 0.15. So just make sure you record all that. You get it. So we're going to go 2.2 times 9.8 minus T, that's 6, sine 24.5. 0.2 times 9.8 minus 6 sine 24.5. I'm getting about 19.1 newtons. Okay. Oh, it doesn't look like we're looking for the Now, we need the normal force to get friction, but it doesn't look like we have to enter in the normal force like last time. Okay, so now we're looking for the work done by tension. So the work done by tension, well, that's going to be the horizontal component of tension. So for me, it's going to be, let's see, 6 newtons. There you go. It's going to be 6, okay, cosine 24.5 times the distance that we went, which was 1.06 meters. So 6 cosine 24.5 times 1.06. Okay, about 5.79 joules. Okay, work lost due to friction. So we found the normal force. The friction force is going to be mu times normal force. So in my case, 0.15 times 19.1. Okay, about 2.87 newtons. Means the work done by friction is going to be the friction force times distance, right? Now, technically it's negative, but we're going to enter in the absolute value of that. So 2.87 newtons times 1.06 meters. That's 3.04 joules. Okay, final velocity. To do that, we have to find the network first. So the network is going to be the difference in your works, okay? 5.79 in my case, minus 3.04. So the network is 2.75 joules. And the network, right, is equal to a change in kinetic energy, which, since you start from rest, is just equal to the final kinetic energy. So the network is equal to 1/2 mv squared. As we've seen time and time again, multiply by 2, divided by mass, square root. 2 times the network over the mass will be how you find your kinetic energy. So 2 times 2.75 in my case, divided by the mass of 2.2 kilograms. So 2.75 times 2 divided by 2.2. And looking at about 1.58 meters per second. Okay, and it worked. Okay, hopefully you're able to get question 4 right as well. If so, let's move on to question 5, horizontal network. Okay, so we've got 5.3 newtons. .5 kilograms. 128 centimeters, which would be 1.28 meters. You're given mu, mine is 0.37. And I think that's it. I think those are good. So we got to find the network and the final velocity. So to find the network, we got to find first our forces. So we got our applied force. You'll have friction, just mu times normal force. You'll have the normal force, and you'll have the weight equals mg. But remember, those two are balanced, so the normal force, right, is also equal to mg. Okay, so let's calculate the network. So what we're going to do is I'm going to calculate some of these forces. So I'm going to find the friction force. That's going to be the same as mu times mg, or 0.37 times the mass, 0.5, times g, times 9.8. So 0.37 times 9.8 times 0.5, about 1.81 newtons of force. So I need that. Okay, so let's calculate the network. I got to calculate the work done by the applied force. That's going to be the applied force times distance, which is going to be 5.3 times the distance of 1.28. 6.78 joules of work. The work done by friction is going to be friction times distance. Technically, it's negative. Okay, so friction, as we found, was 1.81 times the same distance. Okay, sorry, my calculator just died. 1.81 times 1.28, so about 2.32 joules. The network would be the sum of these. Since one's negative, you're technically going to subtract them. So 6.78 minus 2.32 is 4.46 joules. Now, from the network, okay, we're going to find the final velocity based on the network. So network, again, is equal to a change in kinetic energy, which, since you're starting from rest, is equal to your final kinetic energy. So your network equals 1/2 mv squared, and v is 2 times the network divided by the mass. So again, we're plugging into the same thing. So 2 times 4.46 over the mass, which I was given as 0.5. So times 2 divided by 0.5 square root, about 4.22 meters per second. Okay, network about 4.46 joules. Okay, and that's it. There's nothing to question number 5. For the most part, as you can see, these calculations are pretty quick and easy to do. Okay, let's move on. Okay, question number 6. We did it. Let's see, I did not. I think I put in. Now, question number 6 and number 7, we actually worked out in class, okay? So question number 6, we worked out in class. You might remember. Question number 6 looked like this. It was called speed from a work graph, so I'm not going to do this one again, okay? But did I? There we go. Speed from a work graph. Okay, so speed from a work graph is one we worked together in class. So I'm not going to work this one again. This is question 6. Let's move on to question number 7, work from an elastic graph. Okay, work from an elastic graph. And to do that, work from an elastic graph. There we are. Okay, so go ahead and enter your name. So what we're going to be given is we're going to be given a shape, a line, okay, on a force position graph, force versus spring length. So look carefully at the endpoints of your line. My line starts at force of 0 and about almost 129 millimeters, and it goes all the way up to 390 millimeters, looks like 1.8. So I'm going to make a couple dots there. I'm going to make a dot at around 130, roughly. It's like 129, but I'll make another dot at, let's see, 390 and 1.8. Right about there. Connect them. Okay, now I need to use that to find certain points. So it says circle 2 points on the graph, and you're going to use those to find the spring constant. Well, here's basically how it works. If I use my spring force equation, spring force equals Kx. Okay, well, look what I plotted here. I plotted force on the y-axis, and I plotted spring length x on the x-axis. This is clearly a linear equation. That tells you that the slope of the line is your value for K. That's what we're going to find. We're going to find our slope. So for me, the rise is about 1.8. newtons. And the run, we're going to go from here to here. So I'm going to go ahead and subtract those. So about 390 minus, I'll say 129. But keep in mind, that's 261 from here to here. That's 261 millimeters. Got to convert that to meters by moving the decimal 3 to the left. So that would be 0.261 meters. Go ahead and divide those two. 1.8 divided by 0.261. I'm looking at about 6.897 Newton meters, or newtons per meter. Okay, now to get the work, we did this the other day in class, to get the work from a force distance graph, all you need to do is find the area, which you guys can see is going to be triangular in this problem. So you got to find the area of that. Well, that's just going to be, that's simple. You already have the base because that was the run. You already have the height because that was your rise for your slope. Now you just need to go base times height divided by 2. So the base was 0.261 in my case. The height was 1.8. So I'm going to go 0.261 times 1.8. And then I'll take half of that. And I'm getting 0.235 joules of work. Okay, and that worked out well. So you can see these questions are really, really pretty quick and easy to do. You just need to know what to do with them. To find spring constant, so the slope of a force distance graph. To find work, it's the area under a force distance graph. Now our final question is question number 8. And question number 8 is power of motor for building on hill, level 1. Okay, now when you log in, it says in this problem, you'll be determining the power of a motor expending to pull a person up a hill using a tow rope. Assume the ice on the hill is frictionless. You can ignore the energy loss on the hill. So when you're ready to start, click begin. Now, click on show question. It's going to give you some information. Let's write all this down. So we're given the mass of the person in the sled, 98.4 for me. So mass, 98.4 kilograms. Okay, I'm also given the angle of the hill. Theta right here is 18.2 degrees. Okay, the gravitational field for my case is 11.2. So G is 11.2 newtons per kilogram. Don't assume it's going to be 9.8. All right, the poles are spaced 10 meters apart. So from here to here to here, these are all 10 meters apart. And we're going to use that to our advantage. Because what we're going to do is we're going to start the clock, we're going to start the timer when the front end of that is right here or at the front end of a pole. We're going to let the sled go up 10 meters, and then we'll stop the timer right here. Okay, I'll show you how that works. It's pretty easy. Okay, so I'm just going to move all this stuff down here, I guess. Okay, now time the known distance between the poles and use that to find the velocity of the hill. Okay, so let's do that. So now what I'm going to do, I'm going to hide the question for now. Okay, and I'm going to start the motion. I'm going to click on start timer when the front end gets to a pole, like that. And I'm going to reset the timer. I don't like it. Go. Stop. Okay, that's pretty good. So for my case, the distance between, the time between poles is 2.47 seconds. So the velocity, right, is distance over time. So 10 meters divided by whatever your time is. Mine's 2.47 seconds. Okay, so I'm getting a velocity of about 4.05 meters per second. Okay, I'm going to need that. All right. This is the speed going up the hill. Now we're going to determine the vertical displacement of the hill. Here's how we're going to do that. Make a triangle. That distance was 10 meters. If you think about that, that's the hypotenuse. This is your angle, and this is your height. The height is the opposite side of the triangle, which would be 10 meters times the sine of your angle, right? Or 10 meters times the sine of, in my case, 18.2. So I'm going 19.2, take the sine, times 10. So I'm looking at about 3.12 meters high. Okay, now we're going to determine the change in gravitational potential energy based on that height. So the change in gravitational potential energy is going to be mass times g times a change in height, right? So if potential energy is mgh, then a change in potential energy is m times g times a change in height. Well, the change in height is the height right here, so that's easy. So it's really just going to be written as mgh, just for simplicity. Okay, so write down your information. So we have 98.4 times g was 11.2 in my case, times 3.12 meters high. Okay, looking at about 3,438 joules of potential energy. The last thing we got to do is find the power of the motor in watts. Well, that's going to be easy because that's just going to be the work divided by time. And the work is the same as the gain in potential energy. Okay, so the change in potential energy is the amount of work done. So 3,438 joules divided by, remember it took 2.47 seconds in my case, whatever your time was, write it down. And I'm getting about 1,392 watts of power. Once you have all your data constructed and your calculations done, what you're then going to do is you're going to click Enter Answers on the left-hand side. Start with your name, of course. And it's going to ask you speed and power. Okay? So my speed was 4.05. And my power was 1,392 watts. All right, and there you go. It worked out perfect. So for the most part, these questions go fairly quick, okay? The more challenging ones would be the force applied at an angle because the normal force does not equal the weight in that example. So you're going to have to use Newton's first law to figure out how to deal with and find the normal force. But other than that, these work calculations are pretty easy, okay? And the power calculation is extremely easy. Conceptually, we got to think just a little bit. In any event, I hope you guys were able to get these questions done correct yourself as well. If not,